Hey, I'm on. You did 1B, didn't you? Quiz 1B?
What?
Did you do quiz 1B? Did you retake parts of quiz 1 in this class?
Yeah.
Did you get results back?
I get actually it was the same grade. I don't know whether I get grade for that or not because it's the same grade because I made the same mistakes again.
Oh.
Yeah.
Don't have a grade yet.
So we got our quiz 2, right?
Pardon?
The results of quiz 2.
Yes. Did you get it?
Yeah.
Hi, Beth. Hello. Get this.
I'm getting my.
I don't know if she's here.
I'm getting my Gina grades. I was here on Friday all day. Okay, so I took your advice. I pulled 6 aside.
6 out of 150. Oh, big what?
And 4 additional ones that she wanted to grade herself. So I'm getting there. I have like 30, 40 left.
How long do they each take? You got a count. I started setting it down because I would start to look. I would get until
I got it down in like 10 minutes.
Good.
Sometimes I can tell you what I can do. You can just tell.
Those are the longest stuff. It's the ones that are. It's the ones that are good that I can just skip over. Oh, you're good. The ones are like.
Well, for the most part, they're pretty like 90s. A lot of hundreds. Yep, you scored it. Because I was leaning, I was like, you have to talk about 2 family patterns, like whatever it is, and then incorporate course content. So as long as you decide you want to talk about that one content for each, then I'm good with you. Yeah, I don't know. I'm waiting for Thursday to come back to Detroit.
I don't think we're in Detroit right now. There's other shit too.
Well, so Detroit, I haven't started to collect my data over there. Friday, Saturday, Sunday. Then the OA over there.
Yeah.
Because that's our kids' class Thursday. So
So what about this class? You get to I know that. When are you gonna do all these homeworks? Final week? I may not say that certain kind of stuff.
yeah. You and me are going to be best friends finals.
You and me are gonna be copying shit.
Yeah.
What else you got with that?
Well, I only have, I've done back check class. Completely done. Everything handed in. It's just Julia's paper in this class. And I don't have the green.
I have 2 other classes that will be done by Thursday. So as soon as those are done.
We are good. Yeah.
And I have those 2 stuff. I have all this data run, finish all that. I have 14.
Right.
Almost see that. I'm not starting 15, 16.
Hey, get the big chunks out. One frog at a time.
One main effect of the recycling. The 6-term model is sort of an arbitrary 6 out of 7. Does that make sense? Yeah. The good news is that the awful sound coming from the heating system went away since I was in here a couple hours ago. I called and grumbled, and they promised that it would be turned off for this hour and a half, and they're going to turn it back on. And someone else will complain because they'll get cold. But I care more about you than them. Is that a record number of dogs? All right, last topic, today and Wednesday. And it really is everything we've been building towards. If you want causal interpretability, you're going to have to collect these data using your experiment, which for most of us, most of the time, is unlikely. And so the question becomes, what can we do, not really to have causal interpretability, but to rule out confounds? And the basic approach that we take is, that if we can't control it, we measure it and make it part of the model, which can lead to some really complex models. And up until now, we've sort of artificially constrained things, not no more. There's no reason to anymore. You know how to put every interesting kind of variable into a model. Quantitative variables and quadratic, and with just a scotch more English, you could add cubic, which sometimes is important. Most of the time in behavioral sciences, we get away without strong cubic models. You know how to put categorical variables in by coding them. You know how to put interaction terms in. That's all there is, really. The complexity is portraying the model and the results and the really cool story that you have to tell when you do these complex analyses. And that always comes in two forms, one of which is sort of more the way the data analyst talks about it and thinks about it. The other is what they show their audiences. You need to be able to know what each regression weight in a model means. Knowing that it's an incomplete picture, because the model is really more than just accumulated of the unique contributions. We know that. We saw that back when we did this thing, where we showed, well, here's the criterion, and here's 3 predictors, and here's unique contribution of the 3 predictors to the criterion, and there was this sort of, well, what about that? Well, that's part of the model, but it's not something that's a unique contribution from any predictor. The more variables you get into the model, the more complex those variables are, quadratics and interactions and quadratic interactions and all this other stuff. There continues to be an increasing disconnect between the story you get from the whole model and the story you get from unique contributions. And that's why it's so important to be able to plot that model and tell the story from the plot. And when you start drawing the plots, you often have questions about where are the differences that you think you see. Now you got to go back to being able to operate on the model so that you can ask whether there's a difference there and whether there's a difference there by knowing how to code it and how to send it. The cool thing is that with some practice, which we're not going to have time to do in the next 2 days, but with some practice, you can get to the point that you can cast your models and cast your questions in parallel. And that's what we really want. The thing that's going to make today in particular manageable is that last part of the multiple regression weight interpretation that we sort of put off towards the end. The direction and extent of the change in y for a 1 unit increase in this x, holding all the other x's constant at 0. That means that we can look at the model by looking at any part of the model, recognizing that we're holding everything else constant at 0. So if we put age into the model, and maybe we put an age quadratic term into the model, and maybe we put an age interaction term into the model, we can still say, so, what does the motivation by prior experience look like for 10-year-olds? And how's that different for 5-year-olds and 15-year-olds? We can get all these different plots, and that's what we're going to look at today, is we're just going to work our way through a big ugly. And working through is going to have some parts. One, we got to make sure we get everything weighted and coded and in properly. I've got the challenges to homework 15 back to almost everybody, and in almost every case, it was a coding thing. Sometimes it was just a decimal thing. If you don't carry at least 3 decimals, when you start getting into some of those interaction terms, they have huge standard deviations. If you're not carrying enough decimals, those little tiny regression weights get closer to 0 than it should be. All the things. So I've got nearly all of those back. Then on Wednesday, we're going to look at a peculiar version of this complex model that grew out of the first recognition that, damn, we can't control it anymore, which is called ANCOVA. Now, ANCOVA is just a multiple regression model. It's just a general linear model, but the way people who do ANCOVA as opposed to do regression talk about it is different enough that we're going to take a whole day and talk about ANCOVA the way ANCOVA modelers talk about it, which is a little bit different than the way regression modelers would talk about exactly the same set of terms in exactly the same model. It's kind of like, well, you grew up in the Northeast, it's time to pick up a Southern dialect. Okay? So, today, real straightforward, what happens when it gets ugly? Now, the good news is that for the most part, this is basically the same conversation that we had here, where we were able to take quantitative and quadratic and binary and multiple category, put them together in a model. And we could pick any couple of those we want and plot them. One of the things we noticed is when we plotted them, all the lines were parallel. Why? Because even though we had linear and quadratic and groups in there, we didn't have any interaction terms in there. The only thing we're doing today is we're allowing the interaction terms into the model. Okay? Now, here's the one bit of chicken shit that we're going to do today. We are not going to take on the huge argument of what you do when elements of a model don't contribute to the model. Because as you might imagine, and as we've talked about before, there's an argument about that. There's a lot of people out there who were taught and see the model as having two elements. Everything in it contributes. Nothing if added to it would, nothing that I care about if added to would contribute. And according to that way of thinking about things, if a variable's not in a model, if a variable's not contributing to a model, you take it out. We have been taught there's a third element to the real model, which is no other variable, if added to the model, changes the apparent structure of the model. Sometimes when you take a non-contributing variable out of the model, one or two or more elements left in the model are suddenly different. And we have to remember that according to the people who like this approach, and I'm one of them, just because a variable doesn't have a significant unique contribution doesn't mean that it doesn't make that model better in its presence. Because if we only allowed significant controls into our models, we would have very different models than if we allow all controls into models. So what we're going to do today is we're going to decide what variables go in a model. We're going to put those variables into the model. Then we're going to interpret and plot that model. We are not going to go after the war of can we reduce it without changing it. Am I making any sense? Depending upon where you're trained after this and who you're trained by and where they were trained and how much math they have, you might run into people who have different suggestions. Because there is this parsimony idea out there that you should only have variables in the model that contribute to the model, and the definition of contribute is have a regression weight with p-value less than 0.05. The definition of contribute that we've been working with is changes the weight if changes the weight of other variables if taken out. I really like that model, and that's not the model that I was trained on. I was trained on the two-step definition of the model, like almost everybody in my generation was. And so I'm a convert, and you know how converts can be. Even more insistent that they have discovered the one for. All right, so same basic stuff, only now we're going to have interactions, which is cool because, frankly, the plots of models with interactions are cooler than the plots of models without interactions. Two ways you make your models way cooler. Put those interaction terms in and put those quadratic terms in. Because when there's a curve, the curve often changes the story. So continue our study of the relationships among amount and difficulty in exam practice with exam performance, first graduate methods class. We got the program that they're in, experimental, developmental, and clinical, their future employment intentions, quantitative and research, the number of stats courses they've taken before the current one, and the measure of academic performance motivation. We have to get the basic univariate statistics for all of our quantitative variables, because we're going to need those for plotting and for centering. And then we got some coding to do. We're on a mean center all three of our variables. So we have practice mean centered, we have prior stats mean centered, we have motivation mean centered. We've got the quadratic version of each of those. We've got a dummy code for job program. Because the clinical program had the largest number of people, we decided to make that the comparison. The first program dummy code compares the experimental with the clinical. The second compares the developmental with the clinical. Two things you have to know to interpret the regression weight for a model is what that variable represents and what kind of model it's in. Okay. So one of the things you're going to see on the quiz is you're going to see a setup like this where I give you all of my coding, then I give you the results of the output, and when you look at what each regression weight means, to tell me what each regression weight means, you got to make sure that you know what groups are being compared. And once again, the group that always gets a 0 is the comparison group, and then each dummy code has a target group. It's compared to that comparison group. So experimental and clinical, developmental and clinical. We got a dummy code for job interest. Notice we set it up so that the the research interest is 0, the quantitative interest is 1. We've got a dummy code for practice difficulty, where same is 0, 1 is easy. We've got a dummy code for the job interest and practice difficulty. That's 2 binary variables, so we only need 1 interaction term. We're interested in the interaction between the quantitative variables practice and motivation, so we've got all 4 of the linear and quadratic terms in there. And this is something else that I need to warn you about just a little tiny bit. Many treatments of interactions between quantitative variables don't do all 4. They'll do the linear and then pick one of the quadratic by linear and ignore the quadratic by quadratic. I cannot tell you why. Including what I consider the 2 best books out there. And I've talked to both of the people who wrote them, they just, oh, it gets too complicated. So we're going to guarantee that you're always going to run an underspecified model in the name of simplicity. I'm sure there are times that you wish I had spared you that next level of complexity, but when we're trying to explain, this is degrees of freedom, this is math, this isn't sort of, well, we just leave some of this shit out. It's okay. I'll apologize for the complexity and try harder in the future. And we've got practice difficulty, which is binary by the number of practices. So we have a binary by and linear or quantitative, and that's going to take 2 terms because we've got practice difficulty and linear practice and practice difficulty and quadratic practice. So all these damn pieces. And we just sort of blithely whip them into the model. Now, I always stack things just so I've got them sort of organized, and the order that you put them in drives the order that's in the output. Window. All you have to do is put a star. You just start at the comment line. You can write yourself as much breadcrumbing as you want, just put a period. So we've got practice centered and quadratic, motivation centered and quadratic, prior stats centered and quadratic. We've got the dummy coded variables. Here we've got program. Here we've got job interest. Here we've got practice. Here we've got that interaction between job interest and practice. Here we've got the elements of the linear and the quadratic relationship between practice and motivation. And here we have practice difficulty and amount of practice. Good news is, after doing all this hard work, the model does pretty well. We account for about 75% of the variance, which is significant. A whole array of variables, daunting in its size. And the thing you absolutely have to remember is there's interaction terms in the model. So, when we have an interaction term, a lower order term involved in an interaction term, that lower order term is a simple effect, not a main effect. Now, the thing that makes this a little bit more complicated, is that we don't have all possible interaction terms in. So that means some of these lower order terms are main effect expressions because they're not involved in any higher order effects, while some are simple effects because they're involved in higher order terms. You've got to make sure that you're paying attention to whether each term is a main effect term or a simple effect term based on whether or not it's involved in a higher order term. Another controversy that you will run into is you will run into people who say you have to run the complete full model. That if you've got 5 variables, you just bought into 10 two-ways, all the 3 ways, 5 4-ways, the 5-way. Other people, typically people who recognize the challenges of null washout, say only put those interactions into the model that you can defend from the literature, prior results, good sense, something like that. There is no mathematical solution between those two. And the real problem is that people who are in the don't put it in unless you can defend it group run askance to the third rule of the what is a model. Because if you don't put all of the terms, all of the 1-ways, all of the 2-ways, all of the 3-ways, all of the 4-ways, all of the 5-ways, you may be leaving something out that contributes to the model, or worse, you may be leaving something out that doesn't contribute but changes the rest of the model. And there is a certain disparity between the two things that personally I embrace. But the distinction, or the way you work through that, the way you defend that hypothesis, is you recognize the problems with type 1 errors are greater than the problems with type 2 errors. And you recognize that some very cool work has been done starting about the 1950s, which has pointed out that the vast majority of significant 3-ways are type 1 errors. The next biggest chunk were when first discovered type 3 errors. And a vast majority, like around 25%, minority, around 25%, that the first time somebody hit a 3-way, that is still the agreed upon pattern of that 3-way. Because when you get your sample sizes large enough, remember, as sample sizes go up, type 3 errors increase. Because if you have a big enough sample that's not representative, the not representative gives you a model that isn't quite what you should get, but the big enough non-representative model makes it significant. How are we doing? A lot of pieces. We'll have this conversation again. Wednesday. But the idea is that a lot of times the higher order, really sexy effects don't hold up upon replication and further exploration. And so we are particularly comfortable when you get a three-way or even a complex two-way. It's what we hypothesize from the literature. If that's where our comfort zone is, and that's where editors' comfort zones are, and advisors' comfort zones are, and collaborators' comfort zones are, I think it makes good sense to limit the really complex elements we put into the model to the ones that we have hypotheses about. So here we see that practice has a linear but not a quadratic effect. But notice that practice is part of an interaction with motivation. So what we're talking about here is the practice effect for people at the average amount of motivation. Here we have motivation. It has a linear and a quadratic effect, which is fairly common for motivation. The classic motivation curve is the Yerkes-Dodson. Motivation, think of motivation as a kind of stimulation or crank-upness. So you get that not enough, you underperform too much, you again underperform. It's really common to see quadratic terms in motivation effects. Motivation is involved in practice interaction. So this is the simple effect of motivation for the average amount of practice. Prior stats, we can see that we have neither a linear nor a quadratic. Prior stats is not involved in any other term, so these are main effects, not simple effects. We don't know that it doesn't interact with something. I just didn't have enough of a literature to come up with what I thought it ought to look like. So we wanted to control for prior stats. There's a lot of models out there where the number of prior statistics courses is a big predictor of how well you do in a given course. What this now tells us is when you get other stuff into the model, it probably never was prior stats. It was something that comes with that. Counting the number of stats courses is probably like counting the number of practices. It isn't practice per se, it's what happens during the practice. We can see that we get a difference between the clinical and the developmental, but not between the clinical and the experimental. That's a main effect because program is not involved in any higher order terms. Job interest shows an effect with those that have a quantitative interest having a mean larger than the research interest. That's a main effect because it's not involved in any interaction terms. Here's what we came for. This whole thing is a practice difficulty study. This is a practice difficulty program of studies. This is my best mimic of the true experiment I wish I was able to run. Strangely, nobody who's taking a course that counts towards their transcript in the future wants to be in the control group. And so we run it a little differently. Practice difficulty is involved in this interaction with practice. And so what we're talking about here is the practice difficulty effect for the average amount of practice, which is huge. People who got the easier, on average, 20 points poorer than people who did the same difficulty. Left by itself, that's a frightening effect. It's 2 ways. Performance is raised 1%. Keep in mind, this is common advice. You prepare students by practicing them on easier material. It's supposed to enhance motivation, and, self-image, self-esteem. And it may do those things, but without having a positive effect on performance. All the rest of it is nasty interactions. As we know, there's terms there, but they're all relative. How much more is this difference than that one? How much more is this slope than that one? And working through those and articulating them in proper statistical English won't buy you much in terms of understanding them all. I did them for you. But if you put all of that in your pile, if you memorized all of that, if you could sit here and you could blithely and coherently walk through and tell me what every one of those positive, negative, and zero numbers meant, no one would still be able to follow you or understand them all. Very often the analyst is the only one who's really comfortable with that big old set of numbers. So what we need to do is we need to be able to get these things into a portrayal that we can communicate, that we can tell stories about, that we can get other people excited about our findings, using our findings, following our programmatic research with their own, and a graph is worth 1,000 data descriptions. With models this complex, plotting specific nonlinear interaction effects can greatly enhance the interpretation of regression weights. Here's some additional details that further elaborate and describe the model. The interaction of number of practices and practice of difficulty was particular interest in this analysis. So I took the 2 by Q part of the plotter, right, because I've got a 2 predictor variable, I've got a K predictor variable, and I'm going to shelve everything else at its average. Right? Because I'm taking just the regression weight for practice and its quantitative, and its nonlinear quadratic, and the regression weight for the group difference, and my 2 interaction terms, and I'm putting those into the model, and I'm just not putting anything else into the model. Now, if you wanted to, you could write a version of this, and I know people who have done this, you could write a version of this for each of the possible other sets of variables you might want to have. And then you would plug in all of that stuff, and you get back exactly the same plot. Because these are the regression weights holding all the other variables constant at 0. If you decided that you wanted to see what this looks like, well, let's do it this way. So what we're talking about is people who have the average motivation, because that's mean-centered, so that's now 0. Okay. We're also talking about people that are in the clinical program, because that's what's coded 0 in those dummy codes. If we wanted to see it for the experimental program, all we would do is go in, recode that dummy code, so that the experimental group is the comparison group. It would change some of the regression weights, and it would not probably, well, what it would change is it would change the height. The only thing that would change in there would be the constant. There's no interaction term, so it can't change slope or anything else. The only thing it can do is make it higher or lower. We can even tell whether it would make it higher or lower. If we look up here, we see that the experimental, there's a non-significant 2-point difference between the experimental and the clinical. You go from clinical to experimental, holding everything else constant. It drops by 2. So if we went to the trouble to do all of that recoding, this would be 84.292. The whole graph would drop 2 points. How are we doing? If I wanted this for people that had 0 prior stats courses, I go back to my prior stats variable. Instead of mean centering it, I center it at 0. the mean was was 2.5. So if I drop that by 2.5, then 2.5 times that, going down 2.5 times 1.5, even though that is 6. We would expect that whole thing to drop about 6. Make sense? So when I plug in the variables that I just rip out of the model, I just plug in my slope and my curve for number of practices, my dummy code for similar versus easier, and my 2 interaction regression weights. When I pull those out, I am plotting that simple interaction for a particular combination of other values. But I can have whatever I want. If I wanted to see, like I said, put it all together. I want to see people in the developmental program that have never had a stats course before and have a motivation score of 3. Code center, boom. And because none of those terms are involved in interactions with any of these, again, the only thing it'll do is change the overall height. And this is sort of a cool model. It suggests that at one practice, there's no difference. Both get better, but at different rates, up to about 4 practices. And beyond that, this group cascades into the abyss. This group continues to improve. We had 2 quantitative variables, number of practices and motivation. And when we look at those, there's always this sort of, when you're looking at complex interactions. Hey, I got it. Oh, shit, now I got to figure out. And so we got here, and so we see that we have no linear, no linear motivation quadratic, no practice linear motivation quadratic. What we've got here is just the linear practice quadratic motivation. That's the one that pops. Yes?
I find that really confusing. You look at the interactions and some hit and some don't. It's confusing me how we have the discussion about how you have to put the linear and do the quadratic and whatever. So I'm confused by what you're getting when the output comes back and one hits and the other one doesn't. Like, how can you have? I don't understand what those terms.
These 4?
Are. Yeah, the ones where you're doing like a linear, quadratic, and then a linear, quadratic, and
Let me try and do it in this portrayal. If that's not enough, we'll go back to the PowerPoint version of the same thing. Because it does matter. Notice what happens. As practice increases, the relative performance of the middle amount of motivation changes from being closer to low amounts of motivation, being closer to high amounts of motivation. Does that make sense? So at low amounts of motivation, you've got low amounts of practice, the motivation effect is probably that highs more than medium, medium's more than low. At high amounts of practice, the high and medium motivation both perform well and outperform the low motivation. This change in spacing is the quadratic interaction. So. Neither linear nor quadratic. Right? I got no interaction there because I got parallel lines. Right? I got a quadratic. But the curves are parallel. Right? Here's one we have here. This change is the quadratic change in x2 as x1 changes. We go from equally spaced to this 1 to 2. Here, it's the relationship between x and y that is differently quadratic for the different values of x2. That's got no quadratic, that's got a minor quadratic, that's got a major quadratic. This, well, not quite. Here, the change in the spacing is on the x2 variable. Here, the change in space, here it's just a different quadratic here than there. Here, the quadratic is on x1. I can remember really being annoyed at DOS when you couldn't explain this to me better. Like 2 years later, it's like, oh, fuck this. 30 years later, I'm now. All right, let's do this.
So basically, the difference between vertical and horizontal.
Yeah, because what we have here is high, medium, low, high, medium, low, high, medium, low, left to right. Right? But with a different spacing. Here, high to medium is about the same space as for medium to low. Here, high to medium is huge, low to medium is huge, medium to high is not much. Same thing here. So this is differential quadratic on the xy relationship for different values of x2. Here, we're looking vertically. High, better than medium and low, which are equivalent. High, medium, and low spaced. High and medium the same, different from low. And in our case, so then here we've got both of these things going on. Here we've got both of these things going on. If you want to get really intense about it, remember that's quadratic is eventually going to fall back off. And so the nature of the changes here, you see those suckers cross over. That's your guaranteed quadratic by quadratic interaction. Randy Gumby's probably not the best thing. But so the thing to do with a graph, with a complex graph like this, is personalize it. Okay. Where do you not want to be on this graph? Low amount of practice and low motivation. Now I can control amount of practice more than I can control amount of motivation. So if I'm going to give you 2 practices, what's the motivation effect going to be? Pretty big. And pretty linear. If I'm going to give you 10 practices, there's still a motivation effect, but it's now quadratic. Because medium and high are very close together. Low is really different. That shift from a linear motivation effect of 2 practices to a quadratic practice or motivation effect of 10 practices is the linear by quadratic interaction. As this increases linearly, this quadratic changes. If you do this by GLM, the cool thing that you can get out of the GLM is that you can get the group means and the group pairwise comparisons for the categorical variables. You get the means, but they're in the middle of a plot. And people that have gone through the trouble to generate groups will often say, so how well did this group do? Pointing at a spot on a graph will not be as satisfying as saying, oh, look at this table, they did 77. And the group that is comparable to them, except they did the same difficulty practice, they did a 92. And that's why people who like GLM really like GLM, is that you get those group comparisons. Everything else will come out the same. The one thing that you do when we were doing interaction terms in the general linear model, one of the nice things was that you got an F-test of that whole effect. That only works for categorical variables. Because we're putting these 3 elements of the linear by quadratic interaction term in as covariates, as widths, then you still get a separate term for each one. In other words, if you have 2 quantitative variables, you do not get an F-test of their total interaction. The interaction is separated into the linear and the quadratic components, and you cannot meaningfully wedge those together unless you really want to. If you really want to, you can say, I want an F-test of the interaction between motivation and practice. Nothing to it. You take the 4 elements of the interaction of motivation and practice, you add up the sums of squares, you divide by 4, because there's 4 of those, that gives you the interaction mean square, divided by the error term, you have an F-test of the interaction term between those 2. Depends on who you're sitting with 10 years from now.
I didn't really do that, but I did.
See, to a linear algebraist, the important part is that this is the only thing that's there. Everything else is a derivative of it. We have partitioned the variance into these independent components. We can do anything we want to re-express those because they are independent. so we can add them up. Say, I want an F-test of everything that involves practice. I can grab everything in here that's practice. I can add up all the sum of squares, divide by the number of degrees of freedom, do an F-test of that, and that tells me the total impact of practice. If I dropped all of the practice terms out and did an R-squared change F-test, it would be the same F. Because we're asking, what does that collection of things contribute? In ANOVA, you calculate an F for it. In regression, you throw them out and see what happens to the R-squared. This is why we like linear algebra. Because they bring us these equivalencies that are much easier to do than the actual damn math. The other cool thing about working with GLM is that when you want to get a plot of two categorical variables, it's much easier to get that plot out of SPSS than to write an Excel program that plots categorical variables. If you look through the computators for doing the plotting, there's not one in there for plotting a factorial or plotting the interaction between two categorical variables, because you can get that directly out of SPSS. And then you can grab this picture and throw it into Excel. You can grab the picture out of the computator, throw it into Excel. With a little bit of fussing, you can get them so they all look the same in terms of formatting, font, and color, and background, and all that cool stuff. So here we see that there is an interaction between easy versus sane practice and people who are interested in quantitative versus research. The people that have a research interest, we're going to sort of read this from right to left. The people that have a research interest are hurt more by going to the easier practice than the people with the quantitative interest. And if we're going to plot those means, it's really nice that we can run the expected marginal means and find out, here are those means, and here's the pairwise comparisons. And you can see that the practice effect is bigger for the research than for the quantitative. By the way, did any of that help with what you were asking? The single hardest thing that we have done all semester, and is almost the hardest thing that I know within 2 ways, is getting a feel for the difference between the x1 linear, x2 quadratic, and the x1 quadratic, x2 linear interaction. The closest I can come to that, please notice how I'm expressing that. Oh, it's not even in this set, it's in the summary set. I try walking through one. If it's something you do 8 or 10 reps in, you'll go, oh fuck, that's it, that's all there is to it. And then it'll be your turn to join the group who labor painfully to explain it to the next group. But until then, watch your friend. All right, so don't do homework 17 yet, for those of you that are frothy. Because I want to talk about, I want to have this same conversation as ANCOVA on Wednesday. There's only one model. That model gives us a set of regression weights that tell us the unique contribution of this variable to this model when everything else is held constant. Those regression weights tell us what is expected to happen to y prime for a 1 unit increase in this x, holding all the other x's constant at 0. But the language difference between regression people and ANCOVA people can be daunting. Okay? Typically, the reason that we run ANCOVA models, which is an ANOVA with a control, confound, or covariate, is we are begging for a suppressor effect. We are hoping that that null that we got out of the ANOVA is a mistake, and the only reason that we got that as a mistake was that there is some confound that's operating against the independent variable and smushing it. And when we control for that confound, voila, the effect we always hoped for. And this is not unreasonable, because when you take your pet theory or your pet thing into the real world and you want to show people that it works, one of the things you run into is, well, you don't want to randomly assign. Let's give it to the ones who need it most. Right? I've got this cool new way for teaching spelling. Do we run it in the gifted class? No. Do we run it in the mainstream class? No. We run it in the remedial class. Which means that you're running the experimental condition in a group that starts out below the comparison condition. You've got a pre-existing confound that is working against the independent variable. Remember when we were talking about the effect of a confound depends upon the relative direction of the effect of the IV and the confound? Same thing. A completely different language than regression people use. So we will look at those ideas from the ANCOVA perspective and in the ANCOVA logic. In homework 17, I ask you to bounce back and forth a little bit. Here's a model. Ask you some questions that are how regression people would care to hear about it, and then some questions about how ANOVA people would care to hear about it. Because it's a transition that you've got to be able to make often on the fly. Sometimes it's some of each kind of the book. Sometimes they don't even know the different kinds. All right. When we started out this semester, we started out with things that really you can understand after one explanation a little bit of time. We keep building. We're now to the point that it's like, holy shit, I'm not sure if I ever really want to have to do this. The thing that you have really learned this semester, particularly this year, is a tolerance for ambiguity and complexity, which in my model of the universe are the two best predictors of how well you're going to do after you leave these Howard halls. If you cannot tolerate ambiguity, you're screwed. Because you're making that transition from here, this is worthwhile, read this and memorize it, to go find some good shit and figure out what to do next. That's a much more ambiguous situation. It's also a much more complex situation. And one of the forms of complexity that you guys are getting really good at is you can pick up a handout, you can work your way through that handout, and you can get a set of results and do an amazingly good job of turning it into English. That's your future. Because we cannot possibly teach you the stuff that you need to know. You're going to have to continue to teach yourself. And you have done a really good job of that this semester. Because you can take the PowerPoint, you can take the handout, and you produce homeworks. We have only had 11 homework rewrites this whole year. Damn. So that's 17 in here, 14 in the other one, times 58 and 44. So right around 1,400 opportunities, we're sitting at something less than 1%. You have learned how to approach ambiguity and complexity, use resources, and do pretty well. Sorry, this last one's particular sort of booger. All right, get out of here. We'll see you on Wednesday. We'll talk about